charge is the source of electric field, current is the source of magnetic field. We spent the last chapter to learn a bit about physics related to current. In this chapter, we shall always assume that current is flowing unhindered across a wire. We will not draw the full circuit, but just a segment of the wire which is of interest to us. Of course, in reality, for current to flow, we need a power source somewhere, and they all have to be connected in a closed loop. We simply keep in mind the full circuit and that we do not bother drawing it. We shall not worry about the resistance of the wire either. The bottom line is, we will have current flowing across this wire. Magnetic field, like electric field, is a vector quantity. It carries both magnitude and direction. Let's try to visualize the direction of magnetic field from current carrying wire. If electric field originates from charge points radially outward or inward depending on the type of charge used, how do we visualize magnetic field originates from current? Well, first of all, magnetic field does not originate from current. The field circles around the current. Allow me to illustrate this. Remember when we learned about electric field in chapter 3? We detect and study electric field from the so-called source charge by putting the so-called test charge around the source. Similarly, if we want to study magnetic field, we shall deploy the so-called test magnets, a compass or a few of them, for example. We know that at the heart of it, compass is made of magnet. Magnet has two poles, the so-called north and south pole. Under normal circumstances, all the north poles of the magnets inside the compass points toward the north pole of the Earth. This is of course assuming that the magnets do not interact with one another. In reality, they do, especially if the compasses are within close proximity to each other. For argument's sake, let's assume they do not. So all the magnets inside the compasses will point toward the north in unison. But once the current is turned on, the magnets will sense and align themselves along the magnetic field line generated by the current. Now we can see from the alignment of these magnets that the magnetic field line is circling around the wire. As a footnote, I must remind you that the Earth's magnetic field is still existing, but the compasses will experience significantly stronger magnetic field that comes from the source current. We will learn how to compute the strength of the magnetic field from a current carrying wire in a moment. If we reverse the direction of the current, the magnetic field will still circle around the wire, but in the opposite direction. Now, there is a convenient way to deduce the direction of magnetic field based on the direction of its source current. It is technically known as Ampere's right-hand rule, named after the same Ampere guy whose last name became the SI unit of current. As the name suggests, this rule demands the use of our right hand, curled with the thumb sticking out straight to form a thumbs up sign as shown here. I need to emphasize this one more time. You have to use your right hand, even if you are left-handed. We can then align our thumb along the direction of the source current. Then the curl of our forefingers will give us the direction of the magnetic field circling about the wire. Do convince yourself that this rule will still hold if the source current is reversed. Notice that using Ampere's right-hand rule, we can also deduce the direction of the source current if the direction of the magnetic field is known. That's for the direction. Now let's look at its magnitude. Let's say the wire has a length L, and we are interested to find out the strength or magnitude of the magnetic field at r distance away from the source current. Assuming that the length of the wire is much longer compared to the distance of interest, that is to say, we are interested only with the magnetic field close to the source current, it can be shown that the field strength, denoted by capital letter B, with an SI unit named after an American electrical engineer of Serbian origin, Nikola Tesla, is proportional to the source current divided by the distance from the source current. The magnitude of the field will also have to depend on the material surrounding the wire. In electric field, this is reflected by the permittivity property of the material. In magnetic field, this is reflected by the so-called permeability of the material. Permeability is denoted by the Greek letter mu. If the wire is suspended in vacuum, mu will adopt the numerical value of 4 times pi times 10 to the power of minus 7 Tesla meter per ampere, specifically denoted by mu 0. Lastly, there is a factor of 2 times pi at the denominator, which, like the case of 4 times pi in Coulomb's equation, comes from the geometry. So that's it. We learned from this lecture how to compute the strength of magnetic field which comes from a straight current carrying wire using this equation, whereas the direction of the field can be deduced using Ampere's right-hand rule. Don't forget to use your right hand. In the next lecture video, we will learn how to compute the strength and direction of magnetic field which comes from a circular current carrying wire.